Hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. So now let's get started on our set of questions for today's session. Okay, so question 1 just asks, what is the molar mass of N2, which is nitrogen gas? So to find the molar mass of N2, we need to also find the molar mass of a single nitrogen atom. So this is going to be 2 times the molar mass of a nitrogen atom. So these values can be found on the periodic table, so under atomic mass or atomic weight. So if we plug it in, you'll see that the molar mass of a nitrogen atom is 14.01 grams per mole. Okay, so since there are 2 nitrogen atoms in N2, we multiply it by 2 and end up getting 28.02 grams per mole. Okay, so let's see what the junior tutor said. The molar mass is the mass in grams of 1 mole of an element or compound. The molar mass of an element is equal to its atomic mass. The molar mass of a compound, on the other hand, is equal to the sum of the molar masses of the elements that make up the compound. The molar mass of nitrogen is 14.01 grams per mole. Hence, the molar mass of N2 is 2 times 14.01, which is 28.02 grams per mole. Yep, so I can verify that this solution is correct. Okay, so now we can move on to question number 2. So part A says to draw a Lewis structure for the ozone molecule O3. The order of atom attachment is 0, 0, 0, and they do not form a ring. So they just gave a little hint. Chemists used ozone to cleave carbon-carbon double bonds. Part B is to draw the contributing resonance structures, including formal charges. Part C, how does the resonance model account for the fact that the length of each oxygen-oxygen bond in ozone, which is 128 picometers, is shorter than the oxygen-oxygen single bond in hydrogen peroxide, which is 147 picometers, but longer than the oxygen-oxygen double bond in the oxygen molecule, 123 picometers. Okay, so first let's draw the Lewis structure of ozone. So when writing Lewis structures, I like to first find the total number of valence electrons in the molecule. So I'll just say total valence electrons. For 1 oxygen atom, there are 6 valence electrons. And since we have 3 of them in ozone, we multiply this value by 3. So this gives us a total number of valence electrons of 18. Okay, so now I'm just going to draw my 3 oxygens in a line like that. So let's recall that each bond contains 2 electrons. So far I've only written 4 electrons out of the 18. So I'm going to make one of them a double bond. And then I'm going to fill out the rest with all of the lone pairs on oxygen. So this has a double bond. So I'm just going to write 4 valence electrons on the oxygen on the left. And in the middle, it has a double bond and a single bond on its right. So for a full quartet, I'm just going to add a lone pair at the top there. And then for this singly bonded oxygen, I'm going to draw all of its lone pairs. And then I'm going to show the charges for each of the atoms. The one in the middle has a positive charge, and this one at the end has a negative charge. Okay, so now let's count out all the electrons present in this molecule. Counting all the lone pairs, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And now I'm going to count all the electrons in each bond. So there's 2 in each bond. So 13, 14, 15, 16, 17, 18. Okay, so all of the electrons are accounted for. So that is one Lewis structure. And we can also show this oxygen on the left having the single charge, the single bond, and the oxygen on the right having the double bond. So it's basically the same. The one in the middle will still have a positive charge, but this time the oxygen on the left will carry the negative charge. So I can show another resonance structure. If I bring this negative charge down, to get 2 double bonds and all of the oxygens being neutral. Okay, so the last part says, how does the resonance model account for the fact that the lengths are all different? So for ozone in particular, for ozone, there is a mixture of both S and D bonds. So single and double bonds. Just write it out then. So that's why its length is 128 picometers. So hydrogen peroxide it is 147 picometers. And this is because single bonds are longer, typically, than double bonds. So when we have an oxygen molecule, which only has the double bond, it will be much shorter than the length of the oxygen-oxygen bond in hydrogen peroxide. But since ozone has a mixture of both single and double bonds, it kind of puts it in between the two of the other molecules. Okay, so let's see what the junior tutor said. The Lewis structure for ozone O3 is as follows. So they have the double bonded oxygen, and then one in the middle, and then a single bond. The resonance structures of ozone and their formal charges are as follows. Yep, so they have something similar. They also included, maybe I should have also included a resonance structure kind of in the middle. Showing that you could have a partial double bond as well. Yep, so that's basically the same thing I have. And you can show that the double bond can be on the left oxygen or it can be on the right. Or you could have all three of the oxygens having a double bond. And for part C, the junior tutor said ozone bond lengths were found to be 128 picometers. A single bond would have a longer bond length than a double bond, but in ozone, we find that the bond lengths are equal. This means that they are a mixture of single and double bonds. This is why the bond length is less than that of an oxygen-oxygen single bond and more than that of an oxygen-oxygen double bond. Yep, so this solution is correct. Okay, so on to question 3. What is the Lewis structure of krypton difluoride? Okay, so when finding the Lewis structures, I like to first write out the total valence electrons in the molecule. So in the case of krypton, there are 8 valence electrons. And in the case of fluorine, each fluorine atom has 7 valence electrons. And since there are 2 of them, we'll multiply this by 2 to get 14. And then when we add it all up together, you have 22 valence electrons. So first, I like to have my central atom, which is the krypton, and then I'll draw single bonds to the 2 fluorine atoms. And at this point, I like to write down all of the lone pairs on my terminal atoms, which are the fluorines. Okay, so let's recall that each bond contains 2 electrons. So since I have 2 bonds written down, I have 4 electrons in total, and I need 22 in my final structure. But let's count how many lone pairs are on each fluorine atom. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then if we count how many electrons we have written so far, we have 6 on each fluorine and then 2 in each bond. So pretty much 8 times 2. So we have 16, but we need 22 in total. So now I'll just draw all of the extra electrons on the krypton. So starting from 16, we can count up to 22. So 17, 18, 19, 20, 21, 22. Okay, so this is the final Lewis structure for krypton difluoride. Okay, so the junior tutor said, krypton difluoride, or KrF2, is a chemical compound of krypton and fluorine. It was the first compound of krypton that was discovered. It is a volatile and colorless solid with a molecular structure of linear. When reacted with strong Lewis acids, it forms salts of KrF+ and Kr2F3+ cations. Krypton difluoride is a good source of extremely reactive and oxidizing atomic fluorine. For its synthesis, krypton difluoride can be synthesized using many different methods, including electrical discharge, photoionization, hot wire, and proton bombardment. It can be stored at -78 degrees Celsius without decomposition. Its Lewis structure is illustrated below. Yep, so they have the same structure as I do. From the figure at the top, we can say that the central atom has 3 lone pairs and 2 bond pairs. Hence, its steric number is 5, and the electron geometry is trigonal bipyramidal. Yep, so this solution is correct. They also gave a nice summary of krypton difluoride. Okay, so question number 4 is to write the electron configurations of the following ions. Okay, so let's start off with nickel 2+. So when I write down electron configurations for ions, I like to first try to find the electron configuration of the atom if it were neutral. So first, let's look up the periodic table with all of the S, P, D, and F blocks kind of organized. Okay, so the light blue columns is the S block. The green column here is the P block. The middle transition metals are the D block. And the last 2 rows, the lanthanides and actinides, is called the F block. So when we try to find electron configuration, we start at hydrogen and then move across the periodic table from left to right until we get to our desired element. In this case, it is nickel, which is found... Where is nickel? Here. So it has the atomic number 28. So we can also verify that the electron configuration is correct by counting out all the electrons. In nickel, there should be 28. Okay, so just as an example, for this very first atom, I'm going to show the long way to write the electron configuration. But for the rest of the questions, I'll just do it for the shorthand way. Okay, so the long way of writing a neutral nickel atom is, again, to start off at the hydrogen and write the row number, which is 1, and then you write the block number, which is S, and then how many electrons are in the orbital. So there are 2, so we have 1s2. And then we kind of go left to right to the next row. Next row is 2s2, And then jumping over, we write 2p6. Then the next row is 3s2, and then 3p6. And then we have 4s2. And then when we get to the D block, it's going to be the row number -1. So we just write 3D. And then we count up to our desired element, which is nickel. So we count 1, 2, 3, 4, 5, 6, 7, 8. And then we get 3D8. Okay, so this is for a neutral nickel atom. The question asks for nickel 2+. And typically we would take from electrons from the last orbital. But for this case, we will be taking the 2 electrons from 4s2. And this is because partially filled d orbitals are more stable. So now those 2 electrons have been taken, and we can write the new electron configuration, 3p6 and then 3d8. Okay. And then if we were to write the shorthand configuration, to do that, you would just look at the noble gas that comes before nickel. So it's argon. So we put argon in square brackets, which has the same electron configuration as this 1s2, 2s2, 2p6, 3s2, 3p6. And then we just need to write the square brackets and then 3d8. So this is the shorthand electron configuration of nickel 2+. So now let's do the same thing, but for all of them, the shorthand configuration, just to save us some time. Next, we look at cadmium 2+. So again, let's just write down the electron configuration of neutral cadmium 2+. So cadmium is found here, atomic number 48. So first I'm just going to write the noble gas that comes before it. In this case, it's krypton. I'll put that in square brackets. And then starting at row 5. Or krypton. Yeah, okay. So cadmium's right here. And we are going to write 5s2, 4d10. Oh, oops. I wrote it down here. Okay, so again, when we have a filled d orbital, this is more stable than a filled s orbital. So we'll be taking 2 electrons from the s. And the electron configuration for cadmium 2+ is krypton and then 4d10. Okay, so for C, we have zirconium 3 plus and zirconium 4 plus. So the neutral electron configuration of a zirconium ion is the krypton, and then 5s2. So zirconium is right here. 5s2, 4d2. Okay, so when we have zirconium 3 plus, again, I'll take from the s orbital, and if we were to take away 3 electrons, we get an electron configuration of 4d1. For zirconium 4 plus, if we took away 4 electrons, we would get the same electron configuration as krypton. Okay, so now let's do the last question, which is part D. We have osmium 2 plus and osmium 3 plus. So for a neutral osmium atom, it is found here at atomic number 76. So the noble gas that comes before it is xenon. So we just write xenon in square brackets. And then going down, I'm first going to fit in our F block. So if you can see here, it is inserted in between right there. So I'm just going to put my 4F14, and then I'll write down my D block. Next, 5D6, and then 6S2. So I just wrote my S block last this time, just so that it's easier to show how the electrons are taken away. So if we were to take away 2 of these electrons, again, I'll be taking from the 6s2 orbital. So our new electron configuration is xenon 4f14 5d6. And then if we were to take away 1 more electron, it would be xenon 4f14 and then 5d5. Okay, so let's see what the junior tutor said. All the given ions are transition metal ions. Transition metal ions have a unique way if it loses electrons or electron to form a bond with another atom. The outer valence electrons will be the ones responsible for interacting to form a bond, hence the ns orbital electrons. Hence, these electrons form ns orbital will be removed first before the inner electrons, which are the ones in the d orbital. For this question, I'll be using noble gas notation for electron configuration for simplicity. The ground state electron configuration of nickel is argon 3d8 4s2. When it becomes a metal ion in the form of nickel 2 plus, it will lose 2 electrons. The electrons in the 4s orbital will be the ones that will be given up. Hence, its electron configuration now is written as argon 3d8. For cadmium 2 plus, they have cadmium, the krypton 4d10 5s2, When it loses 2 electrons, it is now krypton 4d10. For the 2 zirconium ions, they have ground state electron configuration of zirconium, krypton 4d2, 5s2. So notice that they write the 4d before the 5s. So you can also write it this way as well. And when it loses 3 electrons, it becomes krypton 4d1. When it loses 4 electrons, it just becomes the same electron configuration as krypton. Lastly, for osmium, the ground state is xenon 4f14, 5d6, 6s2. When it loses 2 electrons, it becomes xenon 4f14, 5d6, and then when it loses 3 electrons, it becomes xenon 4f14, 5d5. So this solution is correct. Okay, so question 5. What is the molar mass of lactic acid, C3H6O3? Okay, I'll draw down the structure of lactic acid. It has a carboxylic group, the end there, and another alcohol group. There are 1, 2, 3 carbons. There are 3 plus 4, 5, 6 hydrogens. And then lastly, there is 3 oxygens. So to find the molar mass of lactic acid, we would first need all of the atomic masses of the atoms involved in the compound, which is carbon, hydrogen, and oxygen. So their atomic masses can be found on the periodic table, and to calculate for the molar mass of lactic acid, it will just be 3 times the molar mass of carbon, since there are 3 atoms of carbon in lactic acid. We're going to add this to 6 times the molar mass of hydrogen, plus 3 times the molar mass of oxygen. So again, from the periodic table, we can find their different atomic masses. So the molar mass of carbon is 12.01 grams per mole. The molar mass of hydrogen is 1.01 grams per mole. And then lastly, the molar mass of oxygen is 15.99 grams per mole. Okay, so adding all of these values up, we get a molar mass of 90.09 grams per mole. Okay, so let's see what the junior tutor said. Given the formula of lactic acid, there are carbon, hydrogen, and oxygen atoms present in the compound. Identify first the molar masses of these elements, which can be found on the periodic table. Okay, so then they multiplied these different molar masses by how many atoms were present in lactic acid, and then they summed it all up to get 90.09 grams per mole. So this solution is correct. Okay, so question 6 asks, what's the difference between a formula unit and a molecule? So first I'll just write down the definition of a formula unit. So formula units are the lowest whole number ratio. So this is similar to like the empirical formula. So lowest whole number ratio of a compound with an ionic bond. So recall that ionic bonds are between between a metal and a non-metal. And when we have a molecule, this is when two or more elements or non-metals are covalently bonded together. So an example of a molecule is like water. Okay, so let's see what the junior tutor said. Both molecule and formula units describe the smallest unit of a compound. Molecules make up a molecular compound, which consists of atoms that are covalently bonded. Formula units make up an ionic compound, which is described as the smallest ratio of the cations and anions present in the compound. The difference is that molecules do not represent the smallest ratio of the atoms present in a molecular compound, while the formula unit is in the smallest ratio of the ions present in the compound. Say, for example, you have hexene, which is C6H6. The molecule of hexene contains 6 carbon atoms and 6 hydrogen atoms, which, when written in the chemical formula, is not in the lowest ratio form. Ionic compounds' chemical formula is always written in the lowest ratio form, hence it is always regarded that ionic compounds' chemical formula is always written in empirical formula form. So an example of like formula units, NaCl, it's already in the lowest whole number ratio. Okay, so I can say that this solution is correct. Okay, so moving on to question number 7. Is sulfur dichloride polar or nonpolar? So first, let's write the structure. We have 2 lone pairs on the sulfur, and then on the chlorine, we have 6 lone pairs in total. Well, 3 lone pairs, 6 electrons in total. And we can recall that chlorine is much more electronegative than the sulfur. So we can show non-zero dipole moments being formed from each sulfur-chlorine bond, and the molecule as a whole has a non-zero dipole moment. So let me write down here that this molecule is polar. So this is because the shape of the molecule is bent. So we can see that it's bent because the central sulfur atom has these two lone pairs, causing it not to be symmetrical, so the chlorines don't cancel each other out. So it is bent from the lone pairs on sulfur. And also, fluorine is more electronegative. This causes a non-zero dipole moment Okay, so I'll just also take note that the actual sulfur chlorine bond is polar as well. Since chlorine is more electronegative than sulfur. Okay, so let's see what the junior tutor said. Is sulfur dichloride is a bond between an atom of sulfur and two atoms of chlorine. To determine if it is polar or nonpolar, we have to solve for the difference in their electronegativity. A difference greater than 0.4 means that the bond is polar. Sulfur has an electronegativity of 2.85, while chlorine has an electronegativity of 3.16. So when they solved for the difference in electronegativity, they found that they got 0.58, which is much greater than 0.4. Therefore, the bond is polar. It can be determined by reviewing its Lewis structure. A bond is said to be polar if there is a sharing of electrons. From its Lewis structure below, there is a sharing of electrons between chlorine and sulfur. Therefore, the bond is polar. So this sentence isn't necessarily correct because you can have a sharing of electrons and the bond can also be nonpolar. So an example is like carbon and hydrogen. So they still share electrons, but the carbon-hydrogen bond is nonpolar. So I can just kind of correct them. Sulfur dichloride is indeed a polar molecule. However, the explanation is not necessarily correct. Okay, so I said it is indeed a polar molecule. However, explanation given was not necessarily correct. The reason why the molecule is polar is because its shape is bent due to the lone pairs on sulfur, and that chlorine is more electronegative, causing a non-zero dipole moment in the molecule. The sulfur-chlorine bond itself is polar since chlorine is more electronegative than sulfur. And then I'll also say that a bond can be nonpolar Okay, and then I just also added that a bond can be nonpolar when electrons are shared as well. For example, the carbon-hydrogen bond, it is nonpolar since the electronegativity difference of carbon and hydrogen is only 0.4. Okay, so moving on to question number 8. So what is the percent error of the following measurements? A, the density of alcohol is found to be 0.8060 grams per milliliter. Its true value is 0.7980. And B, the mass of gold is an earring. Earring analyzed to be 0.8478 grams, and its true value is 0.8644 grams. So first, let's write the definition of percentage error. So percent error is the difference between the approximate and exact values and it is useful in finding out how accurate a measurement is. Okay, so for part A, first I'll just write down the equation for percentage error. And this is the absolute value of the true value minus the measured value. So these bonds, these lines kind of show, it means you're looking for the absolute value. So let's say when you have the true value minus the measured value, if it's a negative number, then we are only interested in the positive number. So that's kind of what those two bars mean. So even if the number is negative, we will take the positive value of the number. So this absolute value difference is divided by the true value, and the whole thing is multiplied by 100%. So let's do the first example. We're looking for the absolute difference between the true value, which is 0.7980. Let me make this a little longer, just to show it's not like a 1 grams per mil, minus the measured value, which is 0.8060 grams per mil. All of that divided by the true value, which is 0.7980 grams per mil times 100. If we do the calculations, you end up getting a percent error of 1.0025%, which is pretty good. It's a low number. And now let's do part B of the question. The mass of gold is an earring analyzed to be 0.8478, true value 0.8644. So again, let's take the absolute value of the difference between the two. So we have 0.8644 minus 0.8478 divided by 0.8644 times 100. We end up getting a percentage error of 1.9204%. Okay, so that's also pretty low. Let's see what the junior tutor said. Accuracy refers to the nearness of a measured value from the true value. Because the terms nearness and true value are subjective, it is important to have a mathematical formula for accuracy. Percent error is a numerical measure of accuracy. It is calculated by obtaining the deviation of the measured value from the true value, which is the absolute value of the difference between the two values as a percentage of the true value. Okay, so they have the equation here. For part A, they plugged it into the equation. Okay, so you can see an example of how the values in the middle of the two bars would normally be a negative 0.008, but we're only looking for the difference between the two. So they took the positive 0.008, divided it by 0.7980, and got 1.002%. And for part B, they got 1.920%. Yep, so this solution is correct. Okay, so question 9 is silver nitrate soluble in water. So to answer this question, let's first look at the solubility rules. So these might be given in a question or in a textbook, but basically they are rules that will help us find out whether or not something is soluble in water. So sometimes people like to memorize it, but again, it might be given in the question. Okay, so here is like a summarized version of all the different solubility rules. basically your group 1 ions like lithium, sodium, potassium, and even NH4, they're always soluble. When you have NO3 or C2H3O2, these are always soluble, but there are some exceptions. So for example, let's say we had chlorine, bromine, and iodine. These are insoluble with silver, mercury, and lead, and soluble with any other ion. SO4 minus, soluble with all ions except this whole list. CO3. So this table doesn't have the NO3 that we're looking for, so let's use a different one. It's kind of blurry. Okay, so here. So when you have a compound containing NO3, there are no exceptions. So since we have silver nitrate, we can say that this is soluble in water. However, if we had silver bonded with the chlorine, silver bonded with a bromine or iodine, then it would be insoluble. But because it is bonded with a nitrate, we know that it is soluble. So the junior tutor said silver nitrate with the chemical formula AgNO3 is a form of salt. Based on solubility rules, salts containing nitrate ion are generally soluble. Yep, so this solution is correct. And I think we have time for one more question. Question 10. What are the S block elements in the periodic table? Okay, so it might be easier if I just look up the periodic table with all of the different blocks labeled. So the light blue is the S block, the orange transition metals is the D block. These columns here in the green is the P block, and the last two rows, the lactanides and actinides, is the F block. So let's just write down all the S block elements. So just by looking at the periodic table here, we have hydrogen, helium, lithium, beryllium, sodium, magnesium, potassium, calcium, Rb, I think that's rubidium, strontium, cesium, barium, francium, and I think this is radon, Ra. Okay, so these are all the S block elements. S block elements are the elements located to the far left, including all the elements in the first two columns and helium at the upper right corner. All these elements have valence electrons, which are in an s orbital, spherical shell, and are generally shiny, silvery, soft, reactive metals. Yep, so this solution is correct. Okay, so those are all the questions for today's session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And if you liked today's video, go ahead and give it a thumbs up and a comment. And don't forget to share with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.